thank the organizers and the department for this opportunity to be able to give a brief introduction to the DAE institutes in mathematics in India. And I am not sure how many of you are even familiar with the DAE institutes do mathematics. I mean, people would be associating DAE institutes purely with the nuclear program, and they would not normally even associating mathematics. But it so happens that the DAE has been mainly responsible for the nurture and the growth of mathematics in India. By its two programs, one is called the grant and aid method and another is called the funding method, and I will briefly touch upon what they have done in the grant and aid method and the funding method, and what is really the contribution of the Department of Atomic Energy for mathematics. And in fact, as you would have known, it was Homi Jahangir Baba. When anything about the DAE would start with him, and the Government of India allocation of business rules itself allocates mathematics to the Department of Atomic Energy, and it says all matters concerned with the advancement of higher mathematics, including matters relating to the promotion and coordination of advanced study and research, international relations, grant to universities, grant of scholarship and other forms of financial aid for advanced study and research. This is what the allocation says. And in fact, in the early 1950s, the Government of India gave the Department of Atomic Energy the mandate to support and develop basic research in nuclear sciences and related subjects, including mathematics. Nuclear sciences and related subjects, which includes mathematics. Our purpose here is to survey the considerable contribution of the department in fulfilling this mandate. We begin actually by describing some of the contributions of the aided institutions of DAE to the mathematics, and these activities span a vast swath of higher mathematical education and research in India by the National Board for Higher Mathematics, and we will go one by one. And the aided institutions, the DAE's granting model for supporting research in basic sciences probably sprang from the natural relationship with the Tata Institute of Fundamental Research, Mumbai. That is the one which started. This institute was founded in 1945 with Homi Bhabha as its director and financial support from Sir Dorothy Tata Trust. In the years that followed India's independence, Dr. Bhabha was entrusted by Pandit Jawaharlal Nehru with the task of building India's nuclear program. A key step in this program was taken with the founding in 1954 of the Trombay Atomic Energy Establishment, called the TAEE, which is now known as the BRC, with Dr. Bhabha as the director. All scientific and technical manpower of the TIFR in areas closely related to the design and operation of nuclear reactors moved to the TAEE, from which several other establishments, now collectively administered by the Department of Atomic Energy, eventually involved. The TIFR continued to be devoted to research in basic sciences, has remained an autonomous institution, though fully financially supported by DAE. The success of TIFR perhaps encouraged the DAE to extend the fully aided status to a number of other autonomous institutions. There are at present 8 such institutions in addition to the TIFR spread around the country. And that is the Tata Institute of Fundamental Research. And now you can see the BRC and the IGCAR, Kalpakkam. And now other aided institutions, I am only concentrating on those where mathematics is a major area of research, which include the Institute of Mathematical Sciences in Chennai, Harishchandra Research Institute in Allahabad. And now you can see that atomic energy has various establishments in Chennai and all over the things. I mean, wherever you see, in whichever small area there is a dot, that is an establishment of atomic energy. Therefore, we will start about the Tata Institute, and then we will talk about the Institute of Mathematical Sciences, the Harishchandra Research Institute, and the relatively recently founded National Institute for Science Education and Research, NISER. Like there are various ISERs under the MHRD, there is a NISER in Bhubaneswar, which comes under the Department of Atomic Energy, which is almost equivalent to the other ISERs. Since the School of Mathematics in TIFR was a success story of one single individual by name Professor Komaravelu Chandrasekaran, we will start with that. Professor Komaravelu Chandrasekaran was the person who was really responsible to make the mathematics department of the Tata Institute of Fundamental Research as a center of excellence. And it is under his leadership the center flourished and became a great center. This is Komaravelu Chandrasekaran. Komaravelu Chandrasekaran was born in 1920 at Machilipattinam in Andhra Pradesh. After his schooling in Bapatla, he left for Chennai, which was called Madras at that time, to study at the Presidency College, from where he obtained his MA and came under the influence of Dr. K. Anand Rao. In 1942, Chandrasekaran obtained his PhD from the University of Madras for a thesis written under the supervision of Anand Rao. For a few years after his PhD, Chandrasekaran taught at the Presidency College, Chennai. Around 47, Chandrasekaran left for a term to Institute of Advanced Study in Princeton, which all of you might have heard, for pure mathematics, particularly for pure sciences, particularly for mathematics and physics. That is a mecca. I mean, that is the highest place to which everybody aims to go. That is what is called the Institute of Advanced Study, which is in Princeton. And where he worked with Bochner. And in 1949, Baba hired Chandrasekaran, whom he met that year on a visit to Princeton to lead research in mathematics. The crucial role which Chandrasekaran played in transforming TIFR into a center of excellence. If I want to talk about it, I need a 1 hour lecture separately for it, and therefore I won't talk about that. But for those who are interested, there is an interesting article by Professor Raghunathan where he explains all these things, and therefore I will leave it at that. And Professor Chandrasekaran retired from TIFR in 1965 and moved to Zurich. Now, even though this mathematics which I am really going to talk about is going to be in a slightly advanced mathematics, but instead of again parrot-like repeating, saying that TIFR mathematics is fantastic and they have proved great theorems, etc., I am more or less duty bound to give at least 1 or 2 examples which may be slightly on a higher level. And for the first thing which I am going to talk about, the heroes of Professor Narasimhan and Seshadri, and in fact whatever theorem that I am going to talk about, this is the basis of these theorems, that both of them got FRS around 10 years back. Okay, what is the theorem that they proved? Narasimhan and Seshadri, and what is the theorem that they proved? This topology, this study of the features of geometric objects that remain invariant when the object undergoes continuous transformation. For example, the number of holes punched into a sheet of rubber does not change when such a surface stretches. Thus, the number is a topological invariant of the surface. A basic mathematical concept that lies behind such an invariant is a group called the fundamental group of the surface. It is defined by means of the loops that may be made on the surface through a given point of it. The study of this representation of this group has its roots in the works of the great Jacobi, Abel, Riemann in 18th and 19th centuries. In 60s, M.S. Narasimhan and C.S. Seshadri discovered a fundamental correspondence between the representation of this fundamental group of a surface into the unitary groups and its geometry. That is what is called stable holomorphic vector bundles. This discovery now lies at the basis of the number of pioneering studies in the area of algebraic geometry and mathematical physics. This is one of the great things that they did. 2 natural problems arise from the results of Narasimhan and Seshadri, and in fact the Chennai Mathematical Institute celebrated the 50th year of the birth of Narasimhan Seshadri theorem. I mean, this is the first time I saw that somebody would be celebrating the 50th year of the birth of a theorem, because this theorem really turns out to be the best theorem that came from the Indian soil after the independence. One is to generalize the correspondence to higher dimension surfaces being of complex dimension. The other is to study the family of representative of fundamental groups of surfaces into arbitrary groups. It turns out that the space that parameterizes such a representation itself endowed with the structure of an algebraic variety, and for this reason the problem has led to the discovery of a beautiful relationship between algebraic geometry and group theory. And these last decades have a number of outstanding contributions to these problems through the research of Balaji from Chennai Mathematical Institute, Incidentally this was from TIFR, D.S. Nagaraj from the Institute of Mathematical Sciences and so on. Therefore, this is one of the great theorems that came from the Tata Institute, and probably one of the great theorem that came from the Indian soil after the independence. I mean, when somebody asks what is the great theorem that came, one always talks about the central reversal theorem. The next one I am talking about is so-called open-end conjecture, which talks about what is called a quadratic forms. A quadratic form is something like an x1 square plus x2 square minus square root of x3 square plus x4 square, anything like that in number of variables. A homogeneous polynomial of second degree in n variables is called a quadratic form in n variables. For example, conics are the zero set of a quadratic forms in 3 variables. A classical conjecture of open states that the minimum number of set of values taken by a quadratic form in n variables and z power n must be 0 if the form is non-degenerate and if the ratio of the sum 2 coefficients are irrational number, for example, a form like that. Attempts to prove this conjecture made by a number of famous mathematicians during 1930s to 70s using so-called analytic number theory circle method. And probably again, I don't know how many of you know that this standard method in analytic number theory called the circle method was an offshoot of the methods which were developed by Hardy and Srinivasa Ramanujan to attack the few problems. A new line of attack on open conjecture opened up an observation of M. Raghunathan that a group theoretical assertion on the production of certain orbits would imply this conjecture. This group theoretical assertion was later proved by the Fields medalist. I don't know again how many of you know what a Fields medalist is, and most of you would have known that the mathematics has no Nobel Prize, and therefore people were unhappy that there is no Nobel Prize, and therefore around 1900 there was something else called Fields medal. This Fields medal is essentially given by mathematicians below 45 years and considered equivalent to Nobel Prize. And unfortunately, so far nobody of any Indian has got this Fields medal except one Manjul Bhargava, who is a Canadian American of Indian origin, and there is nobody else. And recently, around 10 years back, they thought they should have something else also, because to restrict the medal for people below 45 is not a very good idea, and therefore they got something called Abel Prize. And again, there we are little fortunate. There is an Indian by name Srinivasa Vardhan who got an Abel Prize. I mean, he is from India. He studied actually in the Indian Statistical Institute in Calcutta, and then of course now he is working in the City University of New York. And therefore, the Fields medal is what is equivalent of the Nobel Prize for us. And therefore, this conjecture of Raghunathan on open conjecture was proved by the Fields medalist G. A. Margulis, who also proved by this method a stronger version of open conjecture, that the values of the quadratic form on the aforementioned type are dense in real numbers. Subsequently, S. G. DAE and Margulis proved that the value of the form taken over primitive integer points are already dense in real numbers. Further, Raghunathan, in discussion with DAE, formulated the far-reaching DAE-Raghunathan conjectures, which generalized his first observation and guided research in this area that involves a deep interplay between group theory and ergodic theory. These conjectures were proved in large part by Ratner in 90s and subsequently by Nimishra in later. Now we have talked about the quadratic forms. This is Raghunathan, who formulated this conjecture and way of how to prove that. I mean, he is also an FRS. I mean, for all this work, he got an FRS. Now we want to talk about the quadratic forms. If one intuitively thinks of the quadratic forms as a degree of freedom, it appears possible that all quadratic forms with rational coefficient and sufficiently large number of variables should represent 0 over rational numbers. That is a natural abstraction to this intuition working out. This may be understood by noting that for any integer, x1 square plus x2 square plus etc. xn square is a quadratic form in n variables, but takes the value 0 only when x is a 0 vector. Taking into this observation, we may ask the following question: is there a minimum number of variables such that every rational quadratic form in this many variables that represent 0 over the real numbers does represent 0 over the rational numbers? This is what mathematicians call what is called the Haas's local global principle. And this local global principle was done essentially by Mayer, Minkowski and Haase and others. And what is very important is in the highly important work completed in 2007, this is one of the again very important work which came from the Indian soil, Parimala of the TIFR and V. Suresh of Hyderabad Central University. They were able to show that any quadratic form in 9 or more variables represents 0 over any field obtained by adding an indeterminate to the periodic fields when the prime P is P from 2, and this is considered again in number theory a great work. But then one has to really talk about the analytical number theory or something what is the Srinivasa Ramanujan type number theory. Now the Srinivasa Ramanujan type number theory was done by a person by name Kalakanagalli Ramachandran, and he had studies in Central College Bangalore and the University of Mysore where he attended for his MSc degree, and he joined TIFR in 1958. In the following year, he attended a famous course given by Siegel in TIFR centered around what is called the Kroneker's limit formula, and subsequently took up this question and addressed it. And in this paper, Ramachandran makes a remarkable application of Kroneker's second limit formula to the theory of complex multiplication, to the construction of certain maximally independent set of units in a given field of imaginary quadratic functions. And that's a work. And these units, which were constructed by Ramachandra in this paper, have come to be known as Siegel-Ramachandra-Robert units. And his work extends. He worked in the Riemann zeta function. Riemann zeta function is actually, at least most of the mathematics students would know, is the important function which you need to study the prime numbers. Therefore, if you want to know anything about the prime numbers, etc., one studies the Riemann zeta function. And many properties of the function have been investigated. Some Riemann hypotheses and some conjectures have still remained unshown. And the other area in which he worked is the so-called transcendental number theory, and this essentially is the numbers which are not the root of the non-zero polynomial equations with integer fractions. This is essentially about the mathematics aspect, but by mathematics one does not mean just the pure mathematics, only algebra, number theory, etc. I mean the mathematics actually extends. Mathematics is useful for any other subjects also, and the DAE institutes have done really a lot for the other areas of other applicable areas of mathematics also. The field of theoretical computer science, which focuses on the mathematical underpinnings of computation, is an exciting and growing field. From 1970s, TIFR Mumbai started a small group of theoretical computer science as a part of speech recognition. Today, the School of Technology and Computer Science at TIFR houses a full-fledged research school in theoretical computer science, which includes applied areas such as coding, information theory, stochastic. And then this theoretical computer science is being done by the other places also, including Institute of Mathematical Sciences in Chennai, where people work on fields of automata, logic, concurrency, formal method, algorithmic game theory, algorithms, applied probability, and various others. And then TIFR also has a school called Applicable Mathematics, that is in Bangalore. TIFR Center for Applicable Mathematics, or it's called CAM, and they do essentially partial differential equations and the various aspects of partial differential equations, which would include nonlinear functional analysis, control aspects of partial differential equation, hyperbolic equations, homogenization, numerical analysis of PDE, micro-local analysis. And then the numerical solutions for simplification, which is very important for the practical applications. The Institute of Mathematical Sciences has led in developing novel algorithms implemented in high performance computers to solve such problems. Important contributions including high Reynolds numbers, high Mach numbers, multi-phase flow, etc. And other areas of mathematical research, which is not exactly mathematics, but where mathematics is used, is entropy based analysis of interspecific script, mathematical modeling of infectious diseases, mathematical model of complex networks, the type of work which is going on in the Institute of Mathematical Sciences. And the quantum information sciences, about which of course the plenary lecture also was mentioning. This is one of the very important areas. And for example, the Institute of Mathematical Sciences is one of the leading centers there. And you go to the third one, the work of Rajaya Simon of the Indian Institute of Mathematical Sciences has become a standard framework, which has already has been cited more than some 1,500 publications. And in quantum information sciences, we are doing really a lot, including communication, computations, and cryptography. And these are the things in which, of course, the DAE institutes are leading functions. And then the other important aspect of mathematics, where it is used to physics, is string theory. And the string theory, the hero is Ashok Sen, who is again an FRS. And string theory is an ambitious program that attempts to give a unified description of the fundamental constituents of matter and forces operating between them. And this technique and results of string theory have had applications to many areas of physics. For example, the work of Seshadri Narasimhan described earlier has close connection with the subject. The work of TIFR group played a major role in understanding two-dimensional string theories. And the mid-90s, string theory underwent a revolution. String theories, TIFR and other DA institutes play a major role throughout and subsequent developments. And the research in string theory exploded in late 1990s. And Indian contribution from that time onwards includes the understanding of the non-supersymmetric stable and unstable states in string theory, construction of string theory models, better understanding of black holes, and discovering new dualities, etc. This is one aspect of my talk, and in the last 5 minutes I will talk about the completely other aspects. This aspect which I was talking about is a so-called grant in aid model, that you find out some institutes which are doing well, or you develop some institute, give a grant in aid and try to develop a good basic research there. The other model which I am now going to talk about is a pan-India model, that the DAE has also been a funding agency for developing mathematics, which as you would have seen as is one of the mandate given in the business allocation. And that is what is called the National Board for Higher Mathematics. The National Board for Higher Mathematics is essentially a funding agency, supports many mathematical activities, and I would think probably unique, in the sense that I don't know whether there is any other country where there is a funding agency exclusively for mathematics. The NBHM was set up as an autonomous body by the Government of India under the DAE in 1983, and since then it has undertaken numerous activities to promote higher level mathematics. For example, through its National Library Committee, the board supports around 70 university and college mathematics and has specifically 12 such regional mathematical libraries. NBHM partially funds various institutions outside the DAE, like the Chennai Mathematical Institute, Kerala School of Mathematics, Bhaskaracharya Pratishthan, the Institute of Mathematics and Application in Bhubaneswar, and Vivekananda University. And this board regularly conducts a nationwide examination to select students from a fellowship program for doctoral studies. Then this which I was talking about the ICM, the Fields Medal, etc. It is given in ICM, and ICM as the only time ICM was conducted in India was in 2010, where this Fields Medal and Neverlina prizes are given, and that took place actually in Hyderabad in 2010, and that was arranged by the National Board for Higher Mathematics. And then there is a Olympiad program which most of you would have known in the high school level, and this Olympiad program for mathematics is supported and trained by the National Board of Mathematics. For example, Subhash Kot, one of the former students of the Olympiad program, was awarded Naval Prize for his work in technical chemistry. Okay, yeah, sure, I will do this. Yeah, this is the one other thing. You know, after the Olympiad, they do the nurture, and this nurture trains them better, and this Naval Prize, the whole world level, was given by Subhash Kot, who was one of the Olympiad guys. And these are the activities of the NBHM, and with that I am finished.